In session 2.1, we're going to start talking about the concept of limits. And limits are really, I always describe them as the engine that drives calculus. They're kind of the missing ingredient that takes us from estimating values to finding exact values. Now, I want to take a look over here at some examples of places where you've seen limits previously and maybe you didn't realize it. For example, in Algebra 2 or Pre-Cal, when you worked with geometric series, you might have had a series where you continuously multiplied by a half. So for example, if you start out with a half taken to the 0 power, anything to the 0 power is 1. And then you multiply by a half again, and 1 half to the 1 power is a half. And you multiply by a half again, and half of a half is a fourth. In other words, 1 half to the second power is 1/4. And you multiply by a half again, and you get 1/8. And you multiply by a half again, you get 1/16, and so on. Well, if you graph this, this is a graph that crosses the y-axis at 1, and then it drops to a half, and it drops to a fourth, and it drops to an eighth. The function is going to do something like this. It's going to get closer and closer and closer to the x-axis. It's never actually going to get there, but it just keeps halving. And 1/32, 1/64, 1/128. It's going to get real close to 0, but it never actually gets there. Okay? We can say that this function is approaching a limit of 0. That is, it's getting closer and closer and closer to a y value of 0, but it doesn't necessarily ever get there. Okay? A function can get to a point and have a limit, but it's really more about what value it's approaching. Okay? Here's another place we've seen a limit. Slopes of tangent lines. So I've got the function y equals x squared, and I want to find the slope at x equals 2. Okay? Well, one way you can do this is you can pick some points. I can find the slope between 2, 4, and maybe I can go over to like 2.1 and find a slope of that point right there. Okay? So you can see I found a slope from x equals 2 to 2.1. That slope's about 4.1. Okay? But I can do an even more careful one. I could go from an x value of 2 to like 2.01, and I could find a slope of 4.01, a little bit more accurate. Or I could pick points even closer together. I could start at an x value of 2 and go to an x value of 2.001, and I get a slope of 4.001. If you notice, these slopes are getting really, really close to a value of 4. And the question is, how do we find out if it's exactly 4, or just kind of getting closer to 4, but it never actually gets there, okay? But again, this appears to be the idea of a limit, the idea of a slope that's being approached. This is getting closer and closer to 4. Whether or not it actually gets there, it seems like our slopes will get infinitely close to 4 at least, all right? So, in this little investigation here, Foerster starts us off with this function. And on the surface, it looks kind of complicated. It's a rational function. It's written in the form of a ratio. Foerster graphs it and asks you to graph it. And on your graphing calculator, this is actually just going to look like a straight line. I'm going to go to standard zoom here, and you pop it in. All right, I have the equation. Looks like a straight line. In fact, you'll notice in Foerster's version, there's a gap in the graph there. We don't even see the gap in the graph there. That gap is when x is equal to 2. And hopefully you can see why there's a problem at x equals 2. You'd end up with a 0 in the denominator. And of course, you can't divide by 0. And so there's one point where this graph is undefined. Okay? Sometimes we call that a hole in the graph. Sometimes we call it a point discontinuity. The term your book is going to use most often is a removable discontinuity for a reason that we will discuss down the road. Okay? So, your graph here on your graphing calculator actually has that gap in it, has a hole, it's undefined at that one value. It's not going to show up on this graph though, because you can get infinitely close to the point where x equals 2 coming from both sides, and there's always another point there. So, because it's an infinitely small gap, your calculator won't actually show that. So, a couple things here. Part A asks you to show that your function takes on the indeterminate form 0 over 0. Hopefully in class we've discussed why 0 over 0 is indeterminate as opposed to undefined. They're not the same thing. Undefined potentially could be a vertical line something like 5 over 0, 10 over 0. Dividing by 0, actually, in a way, you could argue that 0 goes into a number infinitely many times. It's sort of infinity. It's just not a reachable value. 0 over 0 really doesn't mean anything. As a slope, that's a rise of 0 and a run of 0. You're starting at a point you literally don't move anywhere. So anyway, 0 over 0 is a little bit special. If you get a 0 over 0 case, it may look a little bit different in a graph than a case where you get like a 5 over 0 or something like that. We'll see this as we go down the road. So part B says the number 3 is the limit of this function as x approaches 2. Now when we talk about a limit, we're talking about the y value, the output value that a function approaches as you get close to a certain x value. And see that we get very close to a y value of 3 as we approach 2 coming from the left, and we get really close to a y value of 3 as we approach 2 coming from the right as well. Okay, another place you can see this, you can run a table of values. Table on your calculator is really important. So I've got this function in the y equals button here. I'm going to go to the table setup. I'm going to start my table at 2, and I'm going to have it count by ones, all right? And you can see I'm in auto mode, so it'll just generate this table. So let's go take a look at this table. So you can see here that the function's undefined at 2. We can see that there. Notice that as we approach 2, coming from values less than 2, we're getting pretty close to 3. Kind of seems like 3 would be kind of the missing value there based on this pattern. You can see here if we are at values greater than 2, as you get closer to 2, it's dropping down to values of 3. So it looks like we're approaching values of around 3, coming up to 2, and coming down to 2, okay? Now, if I set my table to have a little more precise scale, let's go back to a starting value of 2. Let's make my step 0.01, and let's go look at the table again. So once again, function's undefined at 2, but notice these values here are all really close to 3. I mean, we're up to 2.98, and I'll bet if you highlight it, no, it's just 2.98, okay. Meanwhile, you've got 3.06, 3.04, 3.02, real close to 3. Okay, and I can go in here and I can even make my steps smaller than that. And look how close these values are going to get to 3. As we're coming in, approaching an x value of 2, look at these y values. We're getting very, very close to 3, coming from x values that are less than 2. And also as we come in from x values that are greater than 2, okay? So on a table, that's kind of the idea of a limit, the idea that from x values coming from the left and from the right, we're getting real close to 3. Whether or not we actually get to 3 doesn't matter, but it looks like we can get as close to 3 as we want, okay? So notice here that what this basically says is our function stays close to 3 when x is close to 2, but not equal to 2. Okay. Now, part C asks us how close to 2 would we have to do to keep x within 0.001 unit of 3. Okay, remember our limit looks like it's 3. So if I want to get within 0.001 unit of 3, what we're really talking about here is going up by 0.001, 0001, and going back by 0.01, so that'd be 2.9999. Okay, and the point is I can get as close as I want to 3, and there should be a range of x values that would keep my, actually, you know what, that should be a y, that would keep my y value between those two values, okay? And, you know, you can kind of toy around with this. You can toy around with the table. For example, we're already within 0.002 units, so maybe I can make my step a little bit smaller. Make this 0.0001. You'll look at the table. Start my table out at 2, sorry. And you can see here we're at 2.00030 zeros and a 1 on the x change. On the y change, it's 0.0002. Okay, and you can see that if you go back as well. So I can make my step a little bit smaller. I really need this to be half as big, so I'm going to make my x step half as big. I'm going to make it, instead of 0.0001, which is what I had before, I'm going to make it half of that, which would be another 0 and a 5. And I think now you can see if we go back, I think if you go back and look at the table now, you're going to see, okay, Yeah, our limit is within 0.001 of 3. And on the other side here, I think you're going to see 2.999. Yeah. So now that's kind of a guess and check solution. Obviously, I kind of knew what the answer was, so I picked small values very quickly to get to that goal. You can also solve this algebraically, but I think I want to take a look at that after I take a look at this last part. So part D asks you why this is called a removable discontinuity. Okay? I'm going to go back and look at this original equation. Okay? This is a fraction, a rational expression. And if you think back to pre-cal and other courses, you probably simplified some statements like this. And typically to simplify a fraction, you're dividing a common factor out of the numerator and denominator. And my question would be, can I divide an x minus 2 out of this? What would happen if I address that? So I come over here and take a look at this. I think this is going to factor. Okay? So I'm going to try to factor this. And my thought is, if it's going to simplify, we probably would have a factor of x minus 2 on the top, right? If something's going to cancel from the top and the bottom. So if you think backwards here a little bit, if I had a plus 1 in that position, it would multiply by the negative 2 to give me, oh, let's see, I need a positive 2 there, so I guess I need a minus 1. And to multiply the first two positions to get a 2x squared, I would need a 2x. And I think this is going to do it. So 2x times x is 2x squared minus 4x minus 1x plus 2. Okay? If you take a look at that, you should be able to see that's going to work out to be the original statement. So this thing factors as the quantity 2x minus 1 times the quantity x minus 2 all over the quantity x minus 2. I can divide an x minus 2 out of the top and bottom here, and it leaves me with 2x minus 1. By the way, y equals 2x minus 1 is a straight line. And you go back and you look at our original graph, it looks like a graph of the equation y equals 2x minus 1. It's crossing the x-axis at negative 1. I think if you count a slope off there, you'll find out the slope is 2. Okay? So this original function here that they gave us can be simplified by factoring and canceling out the x minus 2 to leave you with the straight line equation y equals 2x minus 1. Okay? It's going to look a whole lot like that other graph. Now, people sometimes say, oh, the function's simplified to be 2x minus 1. You do have to be careful. This line is solid everywhere, okay? You can evaluate this line at the point where x is equal to 2, okay? The original equation we had could not be evaluated when x was equal to 2, okay? So I would say they're related equations, but they're not the same because one is defined at 2 and the other one's not. But all other points should be the same. So that takes us back to that idea of being a removable discontinuity. You can take out that undefined point and you can get this new function that's defined everywhere. And by the way, then you can find out what that value is. You can put in an x value of 2. 2 times 2 is 4, minus 1 is 3. Remember, that limit was approaching a value of 3. Okay? And so now we can see there, that's where that point would have happened. Okay, it would happen at the point 2 comma 3. So you can actually remove the discontinuity and you can find out what point the function would be approaching coming from the left and the right if it was defined at x equals 2. All right? Now I'm going to take a look at the other two parts of the exploration separately. I'll come back and do those in a different video.